Salam. Today our lesson will be about hybridization. Hybridization. Sometimes it's written in Z instead of S, but for the British it's written in S, and that's not that big deal. First of all, you have to put in your mind hybridization process is mixing between orbitals, different orbitals. So the mixing orbitals that we're going to study are p orbital with S. How can I draw that? And how can I represent this type? By the way, hybridization has a lot of types, okay? And in this lesson, we're going to study the three types of hybridizations. By the way, there are more than three hybridization types, but we will study the SP3, SP2, and SP. After this lesson, you will be able to determine the type, or let's say the hybridization of the atom if you were given an atom with a special type of hybridization. So let's take the carbon atom, for example. Carbon atom has electronic configuration of 1s2, 2s2, 2p2. Good. Which means the p orbital has two electrons. Okay, I'm going to draw the outer shell electrons here. I mean, like in the second shell. We have 2s, okay, that has two electrons. And so, oh my god, this, yeah. And 2p that has, you just remember that p orbitals contains three atomic orbitals, and we have only two electrons in this case. Okay, if you want to write any normal electronic configuration of atom, we can say like this electronic configuration is in the ground state. So if you say, or let's say, hear about like ground state, don't panic. It's a normal case that describes the arrangement of electrons in their normal cases. Okay, the hybridization is mixing between orbitals. S will be mixed with P. How? This electron and S will travel to the orbital of P, and what will happen after that? All of these orbitals, I mean like the S and the three P's, will be in the same level. Okay, I will use another color to describe that, and let's see that. 1, 2, 3, 4, yeah. So we have three p orbitals. These are three p orbitals, and this is the S. Actually, we have one electron in S after removing that electron from S to P, and we have three electrons as you can see in P. In this case, we have four hybridized orbitals. Four hybrid orbitals. Okay. Each hybrid orbital make sigma bond, which means in this case we will notice that we have four sigma bonds. This is the first sigma bond, this is the second sigma bond, the third and the fourth. Okay, another thing you have to put in your mind about the hybridization, the p character, as we can see, we have three orbitals of p, which means the percentage is 3/4 p orbitals, okay, or let's say the contribution of p orbitals is 3/4, whereas the contribution of s is 1/4. Okay, so here we have four bonds of, or let's say four single bonds. The four single bonds are as a result of the hybridization that happened to these orbitals. How can I give you an example about that? As you can see, we have four hybridized orbitals. These four hybridized orbitals make four sigma bonds. In this case, we call this type of hybridization sp3, which means we have one orbital of s, as you can see here, and we have three orbitals of p, and that's why it's called sp3. Let's take CH4, which is the most famous example about the sp3 hybridization. If you were asked to draw CH4, you have to draw it in a three-dimensional structure. So we draw it like we draw the first carbon, and the first bond, as we can see, which is the upper one, and on the left one will be in the same plane of the carbon atom. And two atoms left, right? we have another atom which will be drawn in the dashed line. Okay, we'll draw it like this. All right, and we have another one which is like this, like which. We have hydrogen here, hydrogen here, hydrogen here, and hydrogen here. If I ask you what is the hybridization of this carbon, then you will see we have one bond here, and the second bond here, and the third bond and fourth bond, which means we have 4 sigma bonds. I have 4 sigma bonds, okay, and I don't have any lone pair. Then we have only 4 things around carbon. In this case, the hybridization of this carbon is sp3. Very good. Let's take another example. If we go to C, let's say NH3. If I ask you to determine the hybridization of nitrogen in this case, I need to know what is the hybridization of nitrogen atom. You will draw nitrogen. As we can see, nitrogen has 2 lone pairs, okay, and you will draw it in the 3-dimensional structure. This will be in the same plane of nitrogen, and this one will be like this, which is outside the plane towards you, and this is below the plane, as we can see. So this is the best way to draw ammonia, by the way. Here we have 3 sigma bonds. This is the first sigma bond, this is the second sigma bond, and this is the third sigma bond. But here we have lone pair. We are dealing with lone pair like a bond. So here we have 4 things around nitrogen atom. Then the hybridization of the hybridization of nitrogen atom is sp3, because we have 4 things around the nitrogen. Okay, these things could be sigma bonds or could be lone pairs. So the hybridization of nitrogen here is sp3. Perfect. Let's go to another thing, or another example. If I give you, let's say, oxygen, O, and it has two bonds, okay. By the way, if you want to draw this compound, we draw it like this way. Oh my God, yeah, we draw it like this way, and we have the dashed line, we have hydrogen, we have the 2 lone pairs, as we can see. We will deal with the lone pairs like one bond. Here we have the first sigma bond, this is the second sigma bond, this is the third, let's say, the third issue, or let's say the third thing around oxygen, and this is the fourth one. We are dealing with the lone pairs like we're dealing with single bonds. So the hybridization of oxygen atom here is sp3. And now let's go to the second type of hybridization, which is sp2. sp2 hybridization means we're dealing with one s orbital and 2 p orbitals. We will draw the same thing that we drew in the last time. We have 4 things, okay. We have 1 electron in this area, second electron, third electron, and fourth electron. But as we can see, it says that it's sp2, which means we are dealing with 1 s, okay, and 2 p's, all right. In other words, we have 3 hybrid orbitals, okay. 3 hybrid orbitals means 3 sigma bonds. What about this? What will happen to this? This is unhybrid orbital. The unhybrid orbitals have a mission. They make pi bond. The unhybrid orbitals make pi bond, whereas the hybridized or the hybrid orbitals make sigma bond. How can I represent that? Let's take an example of carbon double bond. As we can see, in this carbon, we have double bond. The double bond is about pi bond and sigma bond. The hydrogen are, as we can see, they are covalently bonded to carbon, and they are also sigma bonds. So we have, in this case, we have 3 sigma bonds, we have 1 pi bond. In this case, we can say the hybridization of this carbon is sp2. Let's take another example like PF3. PF3, as we can see, boron is an element that is in group number 3, which has 3 electrons in its outer shell. It makes 3 bonds with fluorine. Okay, it makes 3 bonds with fluorine. Okay. In this case, this element, by the way, is considered as electron deficient because it has not 8 electrons around its shells. So this element, or let's say this compound, looks like a shape of a trigonal planar. Good. In this case, how many sigma bonds do we have around this element? We have 1, 2, 3. In this case, we have 3 sigma bonds around the boron atom. So the hybridization of boron atom is it's sp2. So it's not necessary to have pi bond. Let's say the main factor, or let's say the main condition is having 3 sigma bonds around the atom. Then you can say like this is sp2. Most likely, or let's say most of the atoms that have a hybridization of sp2 have an angle of 120. So if you were asked about the angle here, it's 120. Okay. So this is for the sp2 hybridization. Let's go to the third type of hybridization, which is sp. I will draw the last thing here. By the way, it's sp. We will draw the same thing here. We have 4 electrons, but we are dealing with sp. One of S and one of P. So only these will be hybridized, which means 2 hybridized orbitals. It means 2 sigma bonds. The unhybridized, they will make 2 pi bonds. Okay, how can I give an example about that? Or let's say, how can I explain that? By the way, the percentage or the contribution of B is half and S is half, or 50-50. Let's take an atom of carbon-carbon triple bond, or carbon-nitrogen triple bond. If I ask you to tell me about the hybridization of this atom, in a triple bond we have 2 unhybridized orbitals, which means we have 2 pi and 2 sigmas. Here we have pi for the triple, and we have another pi, and the middle is sigma bond, and this is sigma. In this case, for carbon-carbon triple bond, we have 2 sigma, and we have 2 pi, then it will be sp hybridization. What about Cn? By the way, sometimes it's written like this, Cn. So when you see any Cn, then put in your mind this is a triple bond. This is alert. Okay, in this case, if I ask you to tell me about the hybridization of nitrogen and carbon, let's take nitrogen. We have double bond here, and we have another double bond in the middle. It's sigma. What about the lone pairs in nitrogen? We consider them as an issue around the atom, so we can say like this is a sigma bond. We have another sigma bond. So for the nitrogen, we have 2 kind of sigmas and 2 pi bond. In this case, the hybridization of nitrogen is sp. What about this carbon? We will do the same thing. We have 2 sigma bonds around carbon and 2 pi, then its hybridization will be sp. Is it necessary to have pi bond? No. Let's take an example of BeCl2. BeCl2 looks like linear molecule, Cl and Cl, and there is no lone pair because Be is in group number 2, and this is, by the way, covalent compound. In this case, B, what is the hybridization of B? It makes 2 sigma bonds, okay? Even there's no pi bond, it's okay, but the most important is the sigma bonds. You have 2 sigma bonds, then the hybridization of Be will be sp.